bit less time than I was hoping to have at the end of these lectures. Today is the day I do the more technical stuff. Obviously, the talks already were fairly technical, and I apologize for that, but this is kind of the technical heart of how we define things. So the key point last time, if you recall, I talked about the notion of what is sometimes called relative convergent invariance, where you have a curve or a stable map having some contact orders with points at mark points with a divisor D. And there are a whole host of problems in trying to define these. Relative invariants were originally defined by a number of people, Young, Ron, and Lee, Jun Lee inside algebraic geometry. And the basic problem you have to deal with is that when a curve such as this degenerates to a curve that falls inside D, it's no longer possible to define the contact orders directly. So somehow you have to deal with more information. The classical algebraic geometric approach of Jun Lee involves doing what's known as degenerating the target. So you have a target space X, and you degenerate the target to allow some maybe P1 bundles over D to be glued on. That has its own technical difficulties because you have to keep track of a lot of data, and you have to keep track not just of the degenerating domain, but degenerating the target. And what I'll tell you today is about a different way of thinking about this in terms of log geometry. So there's no way around it. I have to start with some definitions about log geometry, so I'll do my first half hour of today's talk. So let me just jump into it, give a definition, and then we'll spend a while trying to understand it. A log scheme, or I should say this is due to Fontaine, Fontaine and Kato, K. Kato, in the 1980s. So it's quite old. But was largely just made use of in arithmetic algebraic geometry until probably around 2000. So log scheme is a tuple, right, as X underlined, MX, alpha X. Or what are these things? First of all, X is just an ordinary scheme, which we call the underlying scheme. MX is a sheaf of commutative monoids. X. So recall, we already talked about monoids in the first lecture. A monoid is like a group, but we can't necessarily subtract. We don't necessarily have additive inverses. So these are like the things that have been shown up repeatedly. And the third statement is that alpha X is a homomorphism monoid sheaves. Where OX is given a multiplicative monoid structure. In other words, the operations, multiplication of regular functions, and of course, you can't necessarily invert the regular function, so it is a monoid, it's this commutative monoid. And as usual, I will leave off the word commutative from now on. Okay, so we have one condition. So this is called a pre-log structure. So this data is called a pre-log scheme. And if alpha X inverse of OX star to OX star by alpha X is an isomorphism we have a log scheme. Okay, so this is all rather abstract. What is this condition saying? It's really just saying, so OX star is the set of invertible, or the group of invertible function, regular functions on X. And this is just saying that we have a copy of OX star sitting inside MX. So I take the inverse image of OX star inside MX, so I get a copy of OX star. Okay, so we have to see what this all means. I don't expect anyone, I certainly didn't understand what this meant the first time I saw this. So we also define what a morphism of log schemes is. Morphism of log schemes. F from X to Y is data, first of all, a morphism of underlying schemes. It's just a morphism of schemes, the usual scheme theoretic sense. And secondly, we have a morphism of sheaves of monoids, F flat from F inverse my to mx. So we pull back the sheaf my to mx via this morphism, and then we need to have a morphism of sheaves of monoids, making the diagram F inverse my goes via F flat to mx. Now we have the structure maps with alpha y takes F inverse my to oy, and alpha x takes mx to ox. And we similarly have down here, we just have the ordinary pullback of regular functions. This is part of the data of a morphism of schemes. Right? We have, just put this, this includes a map F star from F inverse oy, ox. That's part of the data of morphism of schemes. So in other words, a morphism of log schemes just enhances this with a little bit more data. We now have a map like this, which is compatible with these vertical alpha maps. Okay, so that should be pretty mysterious at first glance. And now what I want to do is take a little bit of time developing some intuition as to what this is all about. Let's see some examples. Example 0 is the trivial log structure. So this is the triple, or you just take any old scheme, X, you take as MX, you take just the ring of the sheaf of invertible functions, and you take alpha X to be the inclusion of OX star in OX. Okay, this sort of obviously satisfies the axiom. The only property we need is the inverse image of OX star, and here is isomorphic to OX star, but that's obvious. The inverse image of OX star is simply OX star. And this actually allows us to view ordinary schemes as log schemes. Because if you think about what this diagram would mean, if we have a map between two trivial log schemes, this would just be a sub-monoid of this. This would be a sub-monoid of this, which is just the ring of invertible functions, or the group of sheaf of invertible functions. And so, of course, to get a commutative diagram, you would need the map from here to here to be induced by the map from here to here. So this means, so note, a logomorphism x ox star alpha x to y oy star alpha y is the same data as just a morphism from x to y. So this is an extension of a category. In a category theoretic language, this is an extension of the category log scheme of ordinary schemes. Okay, so that's not very interesting. The most important case for us is divisorial log structures. So we take X as scheme, and we take D contained in X as divisor, by which I mean a codimensional one closed subset. And define, oh, so let's let we'll just define it by hand. So define mx by mx of u is equal to f in ox of u, so it's the set of regular functions on the open set u. So u contain x open. Set of regular functions in ox of u such that f restricted to u minus d is invertible. So this is a sub-monoid of ox of u. This is just the set of functions which are invertible away from the divisor d. So you're allowed to have zeros along d, no poles. So this is the sheaf of functions. Functions invertible off of d, away from d. So this is kind of the most basic case. And essentially all the log structures we're going to be interested in will be special cases of this. So for example, if X is a toric variety, and I'll write boundary X, let's take D to be the boundary of X containing X, complement of the big torus, so C star to the N. It's the n-dimensional toric variety. If we take D to be the complement of the torus chart inside X, we obtain a divisorial log structure on X called the toric log structure. Now, what about morphisms? If we have, let's say, D contained in X and E contained in Y divisors, then a morphism schemes F from X to Y produces a morphism between the divisorial log schemes. If and only if the inverse image of E is contained in D. So this is very similar to the statement that a morphism between trivial log schemes is the same as a morphism between the underlying schemes. We think about what we need. Again, in the divisorial log structure case, this is always a subsheaf of this. So all we need to do is make sure that F star takes, to define F flat to be compatible with F star, we just need to know that F star takes elements of this to elements of this. But in the example I just gave, these are things or pullbacks of functions that vanish along E, and we need those, or only along E, and we need those to be functions that vanish only along D. So in other words, we need the zero locus of functions on Y, so in the vanishing along E, to pull back to functions vanishing only along D. And that's why we get this condition. Okay, so you can think of this maybe as a category of pairs. We have pairs X with a divisor, and we have a map between pairs if only if we have this inclusion. So it's not really the usual topological notion of pairs, which would instead require the image of D be contained in E. But... Okay, so that's a simple example. So now let me give you another example, which doesn't fit this category of divisorial log structures. These are known as log points. So let's let Q be a toric monoid. So this is the sort of monoid that appeared when we're talking about toric varieties, i.e. Q is equal to sigma intersect Z to the N for sigma contained in R to the N, a strictly convex rational partial cone. Okay, and now we have the following gadget. I will take K a field. I will take the spectrum of K, so that's just a point. We're working over C, just think of spec C, complex numbers. And then I have as monoid, I have K star cross Q. Since spec K is just a point, specifying a monoid sheaf on a point just means specifying a monoid. I take the K star cross Q, this set of invertible elements in K. And now I have to define alpha X of an element of this product RQ is R if Q is equal to 0 and 0 if Q is not equal to 0. Okay, so it's a little bit funny. But notice that alpha X inverse of K star, see, alpha X of RQ is 0 as soon as Q is non-zero. So anything living in this inverse image of K star must have Q equals 0. This will be equal to K star cross 0. So indeed, that is isomorphic to K star by alpha X. That satisfies the criterion for being a satisfies the criterion for being a log scheme. Okay, so now let me do an example. This is maybe, if you go away with no understanding of what I'm doing today, other than this example, you should just consider yourself as having learned something about this here. So let's think about morphisms. I want to take up to example 3. So consider X to be coming from the divisorial log structure. So I'm going to take A2. So this has coordinates, say, X and Y. And I will take the divisor D be the zero locus of x times y. So D just looks like the two coordinate lines inside the affine plane. And this gives me the zero log scheme. Now let's let spec k dagger be the log point that I just defined up here, but with q equals the natural numbers. The natural numbers here are just start with 0. So that's a good example of a toric moment. So let's ask, what does it mean to give a log morphism from spec k dagger from this log point to x with image the origin in the affine plane? So, of course, if we were just doing ordinary scheme theory, this wouldn't be very interesting. I've already specified the map. We just send the map, the point spec k to the origin, and that's it. That's the only information contained in there. However, because this is not a divisorial log structure, spec k dagger isn't a divisorial log structure, it's not entirely obvious what kind of information is contained inside the log maps. Right, so let's call this map F. And now let's think about the diagram we need to get. So we need to define a map, which we call F flat, from F inverse mx to k star cross n. Now, because F is just a map from a point, it's not hard to see. This is just the stalk of x of 0. So this is germs of regular functions at 0 and a2, which only have zeros along D. And this is the same thing. I want to be very explicit. This is a set of things that form phi times x to the a times y to the b, where a, b are greater or equal to 0, and phi is a germ of an invertible function. Okay, so that's the left-hand side of this map. Okay, well, we have a little bit more, because remember, we also need this commutative diagram. So this should make a diagram. So what's the diagram we need here? We have F inverse mx goes to k star cross n, goes down to O, well, again, this would be F inverse of OX. Which is the same as the stalk of OX at 0, so just germs of regular functions. And that should go to F upper star, this is F flat, this should go to K. And if you remember, the map on the right is RQ gets mapped to R if Q equals 0 and 0, Q is not equal to 0. Okay, so how do we specify F flat? Well, let's note a few things here. So let's look at an element of this germ, so an element up here, of the form just phi, where phi is one of these germs in invertible functions. And let's see what that has to get mapped to over here. Well, this map just takes phi to phi. This is the structure map for x. So let me write this as alpha x. This is alpha spec k dagger. So I can use commutativity here. Alpha spec k dagger of f flat of phi is the same thing as f star of alpha x of phi. Alpha x is just inclusion, so that's f star of phi, thinking now phi is just a regular function on x. And this map here is just evaluation at 0. So that gives us 5, 0. Okay, so there's not much choice about where the map f flat has to go, because in order to get 5, 0, which is a non-zero number, f flat of phi would then have to be the form 5, 0, 0. So thus f flat of phi is equal to 5, 0, 0. Okay, so that tells us what f flat has to do on phi. There's no choice about that. So then we also have f flat of 1. So again, use trigonometry. This is f flat of x. Well, this is going to be something. Let me write it as Rx A. Maybe not A. Rx alpha x. No, not alpha x. What do I choose here? Beta x. Okay, so this is an element of k star cross n. That's just whatever it is, but if I apply alpha spec k dagger, f flat of x, that's supposed to be the same thing as taking f star of alpha x of x. F star of alpha x of x, first of all, this is just, again, f star of x, and that's the valuation of x of 0, which is 0. So that tells us one thing about one constraint on this, which is that beta of x should be greater than 0. Otherwise, if beta x was 0, then alpha spec k dagger would be not 0, but would be Rx. So we have beta x greater than 0. Okay, so it's a natural number, but it's positive. And similarly, f flat of y will be some pair ry beta y with beta y greater than 0. And this completely determines f flat, and any choice within these constraints gives you a commutative diagram here, satisfying all requirements. So easy to check. Exercise. Check that given pairs Rx alpha x, Ry beta y, with Rx Ry in K star, alpha x, alpha y in n greater than 0, we obtain a logomorphism f from spec k dagger to x. So all you have to do is define f flat by decreeing that, well, necessarily f flat of invertible function, just gives you this. F flat of x is given by this data that we've chosen, and F flat of y is given by that data. Together, that completely determines F flat because it's a monad homomorphism, and x, y, and these invertible elements phi generate the monad. Okay, so conclusions, there are a lot of logomorphisms. So there are two bits of data. One, what I would call discrete data. Namely, i.e., the pair beta x, beta y lives in n squared, and neither allowed to be zero, so it's actually I'll just write beta x times beta y is non-zero. And secondly, continuous data. Rx, Ry in k star squared. Okay, so there are a lot of logomorphisms. There's lots of information hiding inside a logomorphism just from the simplest possible non-trivial point you can think of into the origin of E2. So that should be part of the takeaway of the basic definition. Okay, so that should hopefully at least convince you that this category is pretty rich and contains a lot of potentially extra information. Now I need to do a few more technical things. I need to talk about full backlog structures. And this is generally, I think, when things start to get a little bit hazy in people's minds. So remember, I defined a notion of pre-log scheme when I was defining a log scheme. So if x, nx pre, I'll just decorate that alpha x, the pre-log scheme. So in other words, alpha x need not induce an isomorphism between the inverse image of OX star and OX star. We have an associated log scheme. So the idea is that you can essentially put in a copy of OX star, and you do that by defining MX to be MX pre direct sum OX star. But now there might be some, it could be that some piece of OX star is living in here. So what you do is you divide out by essentially the submonoid consisting of pairs P alpha x of P inverse, where P is an element of alpha x inverse OX star. So in other words, what I do is identify, what this does is it identifies P with alpha x of P, provided that alpha x of P is actually invertible. Okay, so this is just a way of sticking in a free copy of OX star. And anything in MX pre which maps to OX star is identified with the element of OX star. And then we define alpha x. I should put a pre there. And maybe not. Find alpha x from MX to OX is given by alpha x of a pair P phi gets mapped to alpha x of P phi. Okay, That's good. So I can go for, so somehow this distinction between p-log structures and log structures isn't so important. Why do I want this at this particular juncture? Well, I have pullback log structures. So suppose given a morphism, fx to y of schemes and a log structure y and y alpha y. Suppose we have a log structure on this scheme. Then I can pull it back to x. So f star and y is a log structure on x associated to the pre-log structure so I just take alpha f inverse my. Now f inverse my has its map to f inverse oy. And then I also have the more underlying morphisms of the map to ox. So this map here is a map from this sheaf of monoids to ox. It may not define a log structure, so we have to take the social log structure. Okay, so this I think is always somewhat difficult to always difficult to sort of understand what's going on. I want to be honest with my definitions, which is the main reason for giving it at the moment. The main point is I want to now restrict the type of log structure I'm considering. The definition. A log structure or a log scheme, X, is fine if locally on X, there's on some open cover of X, if locally on X, there exist charts so these would be maps from some open subset of X to spec K back P, where P is a finally generated integral monoid. Okay, so now I have to define an integral. So this means cancellation rule holds i.e. if P plus Q is equal to P prime plus Q for elements of monoid P, we have P equals P prime. So I can cancel. Of course, if it was a group, you could just subtract Q from both sides. But these need not be groups. Okay, so this is essentially a toric variety and therefore carries a toric log structure. So this carries the toric divisorial log structure. And what does this do for us? The pullback of the log structure, of the toric log structure. On spec K bracket P is the log structure on U. Okay, so again, this might seem a little bit technical, but you should think of it as follows. So if you're interested in manifolds, you might first define topological spaces. Topological spaces are very, very bad gadgets in general. You can think of all sorts of perverse topological spaces. But then you define a manifold as something that locally just looks like an open subset of Rn. So here you should think similarly. A general log scheme is some awful thing. There might be very little control over the sheaf of monoids and X. On the other hand, the log structures on toric varieties are very nice, well-behaved things. And so now we define, we say log scheme is fine if locally the log structure is pulled back from the toric variety. Now, one more definition, and then we'll get on to sort of hopefully see why we're interested in all these things. So we say X is fine and saturated if P can always be taken to be a saturated monoid, i.e., we've seen this before. Whenever well, let's see. Let me just say, simplify life here, i.e., spec K bracket P is a normal toric variety. So I think all the toric varieties we discussed so far in the lectures were normal. We always got monoids from this construction. You start with a cone, rational modular cone, you take the dual cone. That's always a saturated cone, always finds a normal toric variety. But sometimes people like to think about non-normal toric varieties where P might be something like, let me do a quick example, e.g., P equals 0, 2, 3, 4, and so on, inside N, not a saturated monoid. As K bracket P, or spec K bracket P, that's spec of, this is two generators corresponding to the generators 2 and 3 of the monoid, and they have a relation which is x cubed equal to y squared. So that's a nodal cubic, which is non-normal. So we have this extra adjective here, which tends to show up everywhere in log geometry. Okay. One of the great things, so now let me come to what is really perhaps the punchline about log schemes.
Sorry, Mark,
Yeah.
could I please interrupt with just one question?
Yes, of course.
So this this definition, as you've stated it implies that any log scheme that is fine is necessarily, the underlying scheme is necessarily rational, is it not?
No. So all we require is that we have maps from U to the toric variety. Right?
Okay. So these are just maps, not isomorph.
Definitely. Yeah, arbitrary, this could just be, your favorite crazy variety mapping to a single point in here.
Okay. Yeah, thank you. And also, is it clear from this definition that divisorial log schemes are fine, or is it even true that?
No, it's not true in general. If you have some bad singularities, that they may not be fine.
Okay. Yeah. Thanks. Thank you.
Yeah. Yeah. Okay. So, what is really the punchline here? So, key point. In the category of fine and saturated log schemes, let me write this just as abbreviate this as FS, which is standard in the literature. Category of FS log schemes. There's a notion of log smoothness, which is defined in analogy, in analogy with ordinary with ordinary smoothness of morphisms. F from X to Y. So if we have, here I'm underlining these just to make clear we're doing schemes. There's a notion of smoothness in algebraic geometry. It doesn't mean C infinity. It means that, for example, the fibers of this map are non-singular. That's one of the implications. I won't write down a definition of smoothness because it's a little bit technical and doesn't really help you anyway. But smooth morphisms will be flat, for example, and have this non-singular fibers. So there's this notion of log smoothness, but log smoothness somehow allows certain kinds of singularities. So I can then, without giving the definition of log smoothness, let me do some of the crucial properties. So this gives, so if X is a toric variety, well, actually, let me just say this in a slightly different way. If, let's say, theta from P to Q is a homomorphism of toric monoids, let me just be, let's say, homomorphism, injective homomorphism. Sorry, let's check the. Sorry, I didn't write down in my notes the right condition. Let's just say injective homomorphism of toric monoids. Then the induced map from spec K bracket Q, spec K bracket P, is log smooth. Okay, so here, of course, we get induced map of rings. How does that map of rings go? K bracket P is mapped to K bracket Q just by taking Z to the P. Z to the theta of P that induces the map of rings. And then we take spectra, so the map goes the other direction. Okay, so again, these are with the toric log structures, everything other than toric log structures. So, for example, take P to be 0, we get spec k bracket q to spec k is log smooth. So this is a way of just saying, in some sense, is that this log structure makes this torque variety look as if it's smooth, non-singular. So this makes spec k bracket q behave as if it was a non-singular variety. In general, torque varieties need not be smooth, need not be non-singular, but in the log world, they become non-singular. Another example is I take p equals n, let's take q equals n squared, and theta is just defined by theta 1 is equal to 1, 1. So this induces the map A2 to A1, given by xy goes to x times y. And this is also log smooth. And notice this has a singular fiber. Over the origin, you have the union of coordinate axes. So this gadget here can now be viewed as non-singular also. So this is non-singular in the log world. So this is probably one of the most powerful aspects of log geometry, is it allows us to treat many singular objects as actually being smooth. So let me give you the key example here. So a log smooth family of curves, definition. Log smooth family of curves flat morphism, flat log morphism, pi from C to W of FS log schemes such that, sorry, let me remove the word flat here. I have to be a little bit careful. First of all, the underlying morphism is a flat morphism of schemes. And maybe projective, but maybe proper. So the fibers are compact. Secondly, all fibers are reduced. So we don't allow something like, if we had xy goes to x squared y here, then the fiber over the origin would be the zero set of x squared y, which would be a non-reduced scheme, no potence. And then finally, we demand that pi is log smooth. Sorry, I forgot to add something here. Didn't say anything about these things being curves. These fibers are reduced curves, one dimension. So let me give one example of this, of what this might look like over a log point. There's a classification of such things. So you might have something that looks something like this. So we're allowed to have nodes. The nodes arise, as we already saw, we can have nodes over here. These curves will be nodal. The log smoothness imposes the nodal condition. Whereas when we were talking about ordinary Gromov theory, we put the nodal condition by hand. There can also be various marked points. And some marked points here, P1, P2, and so on, and then we have nodes Q1, Q2. And the map pi might just live. In this case, I want an example where W is just a point, so this would be spec K with monoid K star across Q. Okay, so you have several features here. So it's a little bit difficult. So I want to describe MC. It's a little bit hard to describe MC because there's a lot of continuous data in there. So instead, I'll define some combinatorial aspect of this. Let me define M bar C to be MC modulo the inverse image, alpha C, alpha inverse C of OC star. So this gets rid of kind of the continuous data of invertible functions. Remember, this is a subsheet of this by assumption on the definition of log scheme. And this is kind of residual combinatorial data. So if I look down here, for example, M bar W, that would just be K star plus Q modulo K star cross 0, and that would just be the monoid copy of the monoid Q. So this sheaf captures some of this combinatorial information, throws out the continuous information. Now you have various bits of, I'll describe what M bar C does. So we have also the generic point. So if eta is a generic point, eta is a generic point, so of C, then M bar C eta, the stalk of the sheaf at point eta, will just be Q. That's inherited from down here. If P is a marked point, that's one of these points, then M bar CP is Q plus N with pi flat inducing the inclusion Q bar, like inclusion pi bar flat Q. So remember, pi flat has to pull things from here up to here. That goes from Q to Q plus N, just the obvious inclusion. And then finally, we have nodes. Color here. Yeah. Use a node. Oh, I just realized no one, you forgot to mention turning it over. If Q is a node of C, then M bar CQ takes somewhat of a special form. It's Q plus N squared. So this is Q plus N squared modulo an identification, where this identification identifies something in form 0, 1, 1, gets identified with rho Q 0 for some rho Q in Q. And you can think of this as a combinatorial version of the formula. There's a local equation for C of the form x times y is equal to Z to the row Q in A2 with coordinates X and Y cross spec K bracket Q. Okay, sorry, that's quite a lot of information. Let me pause for questions, and then we should have a little break. Okay, so as I said, this is the kind of curve that we need to want to think about. So yeah, here in this example, this is just a curve over a point. So you should think of this as a nodal curve that has some more information, which is largely combinatorial like nature. And in particular, these curves have three sorts of points. They have sort of general points where the monoid is Q. They have these mark points when the monoid jumps. You can think of that as saying, we're going to include a little bit of extra divisor or log structure where we can allow functions to develop zeros at these mark points. And then finally, we have the nodes, and there the structure is a little bit more delicate to take into account the fact that you do have a singularity curve, and the log structure has to be complicated because it fixes that singularity. Okay, so now let me show you a different way. So, don't worry too much about all of this data I just went through here. Let me show you a different way of visualizing this. So let me introduce the notion of tropicalization. Of a fine FS log scheme. Okay, so for each point, let's say X, MX, alpha X, a fine log scheme. For each point X and X, we have a cone. So I have this sheath M bar X, which I just defined. We divide out MX by the invertible functions. And I take the stalk at the point X, and I dualize this. I take sort of monoid homomorphisms from M bar X, X into R greater equal to 0, where this is the non-negative real axis with the monoid modeling addition. So this is just a cone. So this is, well, I should say we have the rational polyhedral cone. Which I'll call sigma X. Now, another thing we have is if X is in the closure of the point Y, okay, if you're not that comfortable with schemes, this is going to look a little bit strange. But in scheme theory, there are these things called generic points corresponding to non-maximal ideals, and it's possible that a point by itself isn't a closed set, but you can take the closure. So if X is in the closure of point Y, here's what we call a generalization map. Sometimes called a specialization map. And this goes from M bar X, X to M bar X, Y. And what is this map? Well, an element of the stalk is just a germ of an element of M bar X. And so this is U is a neighborhood of X, and S is an element of, well, a section of M bar X over U. Now that gets mapped to the same thing. The point being that now Y is necessarily also an element of U. The fact that Y is in the closure of X means that any set containing X, open set containing X also contains Y. The US can be viewed as a germ, as an open, a germ at Y, as well as a germ at X. That gives us this generalization map. And then dually, we get a map of cones. Which will go from dually, goes from sigma Y to sigma X. And in fact, it turns out to be an inclusion of faces. So this gives us a bunch of cones and face maps between them. And now we can just glue them together. By gluing these together, we get a cone complex, which we write as sigma of X. So let me do a couple of examples here. So the first example is to take X to be A2 with V of XY, with the divisorial log structure. So what does M bar look like? So over here, let's take this is given by Y equals 0. Over here, sections of MX look like phi times some power of Y. Over here, sections look like phi times X to the A times Y to the B. And over here, sections look like phi times X to the A. Now, so if we divide out by invertible functions, what we get for M bar, so here I'm just describing MX. On M bar, at the level of M bar, all I do is I remember the exponents here. So I have on this axis, I have a copy of N, remembering the order of vanishing, if you will, of a function along here. On this axis, I again have an N, remembering the order of vanishing, or the exponent of the function here. Then at the origin, I have an N squared, because I have two possible exponents to worry about. So that's what M bar X looks like. And if we think about the generalization, so if you have a general point or a generic point to one of these axes, get a map to N. And what happens, you can think about this much more easily at the level of MX. Think about this function and restrict it. So this is defined in some neighborhood here. Restrict it, the generic point of this axis. Well, X is non-zero generically. So X to the A becomes an invertible function in a neighborhood of that generic point. So this becomes an invertible function. You're just left with the exponent B. So in other words, the map really going this way is that phi times X to the A times Y to the B becomes an invertible function phi times X to the A times Y to the B. Similarly, if we go this way, this can be thought of as phi times Y to the B times X to the A. So these two maps here become AB gets mapped to B and gets mapped to A. And if we dualize these two maps, we just get maps from R greater equal to 0 to R greater equal to 0 squared, and R greater equal to 0 to R greater equal to squared. And these maps are just the face inclusions. So namely, A gets mapped to A0, and B gets mapped to 0B. So if I were to draw this, we have the first quadrant and the inclusions of two faces. So in this case, the cone complex isn't very exciting. It's just the first quadrant with its two faces. So that's the first example. The second example, if X is a toric variety, not too hard to convince yourself that sigma of X is the fan for X, viewed as an abstract cone complex. So this is as when I was talking about the, remember I defined this BP last time associated to a pair XD. This is exactly the same thing. It's an abstract cone complex. Okay, so finally, let's think about what happens when we tropicalize a curve. So now let's look at some picture like this, sitting over W with respect K with K star cross Q. So sigma of W, that's pretty easy. That's just, I'll write as Q dual R. So I take the real cone generated by Q and dualize it. Now this is Han Q into R greater or equal to 0. So this is some kind of cone. Maybe it'd be easier to say Q equals N in this example if I'm going to draw pictures. I may get Q equals N, and then I have just a ray. I'm going to draw a picture. Okay, so now what happens is that for every irreducible component, remember, generically along an irreducible component, you just have a monoid Q. So you're just going to get another copy of the same cone. And what you get then is, so for each irreducible component, you get a copy of Q dual R. It's going to land over here. So for each irreducible component, Q dual R, we get, sorry, irreducible component of C, we get a copy of Q dual R. And sigma of C. So for each marked point, we get a copy of HOM Q plus N to R greater equal to 0, which is Q dual R plus R greater equal to 0. So we just get this extra one-dimensional factor. So here, if I were to draw a picture, I have two marked points, and this is going to give rise to two quadrants, which attach to, again, it's a little bit, let me make a better effort to draw this. Oh. Two extras for flaps that have been attached to this. Then finally, for each node, we get a I'm going, without going into the details of how to derive this, but follows from this push-out description, we get a family of line segments over Q dual R. So we get something at one dimension higher than Q to R, and at fibers it has a map down to Q to R, with fibers being line segments. So what we then fill in is we then get this extra cone here, and we also have from this node, we have a cone that does something like loop around here. So the main point is that I have this tropicalization construction is factorial. So I have a map. This is pi. I have a map, which is the tropicalization of pi. And the fibers now look something like fibers of sigma pi are tropical curves, i.e. graphs with bounded edges and unbounded legs. In this particular example, a fiber looks something like this. We have one point for each irreducible component. We have an edge, bounded edge for each node, and those edges connect the vertices corresponding to the different irreducible components. And we have an unbounded leg for each marked point. So these are the nodes. These are the irreducible components. And finally, these are the corresponding mark points. So generally, this tropicalization is the best way to sort of think about the discrete information contained in a log scheme and for log morphisms. There's, of course, continuous data, as we saw in the example of map from spec K dagger into A2. We have continuous data, and the tropicalization doesn't capture that, but does capture the discrete data. Okay, so finally, well, let me say this is what we call, well, I did say this is a tropical curve. Okay, so now I'm finally ready to define the key notion of a stable log map. So in ordinary Gromov theory, we had the notion of a stable map, and it was the modular space of stable maps that led to Gromov invariance. So definition. Stable log map. So fix log smooth target space. X. So stable log map in the diagram. E pi to X F. Where, first of all, C W is a family of log smooth curves, as I defined earlier. And so with marked numbers, so with marked points. P1 through Pn. And let me emphasize that the marked points here are intrinsic to the log geometry. We saw the marked points as points where the monoid Q jumps to Q plus N. And the log structure gets a little bit richer. And secondly, the underline family of maps is a stable map in the ordinary sense. So this is not too much more complicated definition than the original definition of the original definition of a stable map, and now we've decorated the everything. We've decorated the target space, we've decorated the curves, we've decorated the base of the curve, family of curves, all with log structures. That will mean that these log morphisms, as we saw, might carry additional information, like a richer information. Now, one of the key points is that this will carry some information which we call contact orders. So, stable log map is the information of contact order at a mark point. So let's fix a mark point P in one of these domain curves and look at the map. So we have a map F flat. That's supposed to go from F inverse of MX to MC. And this will induce this induces a map, which we'll also write as F bar flat, from the stalk of M bar X at F of P to the stalk of M bar C, a stalk of M bar C at the point P. And this, recall, is, well, it's the same as M bar W at pi of P. That was what was plane Q in my example, plus N. So we have this extra N factor. And now we have projection onto the second factor. So this composition, this map's F bar flat, the composition I'm going to write as UP. UP is a map from this stalk here to N. And this is called the contact order of F at the point P. So this is, again, purely combinatorial information. Notice this is a point. An integral point of the cone sigma F of P. Right, this sigma F of P, this is HOM of M bar X F of P into R greater or equal to 0. So it is a linear, it's a group homomorphism, or monoid homomorphism from here to R greater or equal to 0, which happens to be take values in N. So it gives you an integral point. Okay, so again, this is just combinatorics, but what does this really mean? Let's see an example of this. Example. Let's let X be smooth or non-singular in the ordinary sense. D contain X as non-singular divisor. And put the divisor log structure on X. Okay, so let me draw a picture of that. We have X here, and now we have the divisor D. And now let's take a curve, maybe with, let's make life easier for ourselves, a curve C with one mark point. And this will be just over the trivial log point. So log point just with the sheaf of monoids K star. So the only thing that happens is that this is actually the C is just the log scheme with the divisorial log structure coming from P. And now, if I map by F to some, maybe something which looks like that, notice I have a map of pairs. So now F defines a logomorphism CP to XD as long as the inverse image of D is contained in the divisor defining the log structure here, namely is contained in P, in just the singleton set P. So in other words, this will give you a logomorphism as long as the only point of C mapping to D is the point P. Okay, so there's an instance of a stable log map, as long as this map itself is stable, which it should be. There's no contracted components. Now let's understand the contact orders. So here we have, let's take a function. So in a neighborhood here, I can take a function t. So t equals 0. It's a local defining equation for d near f of p. Then f composed with t, t composed with f, is a function on C in a neighborhood of P of the form, let's say V, phi V to the A. Phi is an invertible function. And V is a local coordinate centered at local coordinate on C, vanishing at P. Okay, so we have this function T. This pulls back to a function in neighborhood here of the form phi times V to the A. These things are elements of MX and MC, respectively. So it's easy to see what happens on the level of M bars. So thus, the induced map level of M bars is, well, we have F inverse M bar X, which is just N at the point P, goes to, maybe I should have said F, try this better. So we have N bar X at the point F of P, that's just N. M bar is just recording the fact that there's one divisor here along which function vanishes to some order. M bar records that order of vanishing. And that maps by F bar flat to M bar CP, which is also equal to N. And this is just 1 goes to A, where A is this exponent here. And this is then the contact order, right? This is UP by definition. We don't have to project anything here because W, the monoid associated with W is 0. So here A is the contact order as I defined it in last lecture. So UP is the contact order as defined in the last lecture. So there's several good things about this. So the first point, so note, first of all, this generalizes and keeps track of contact orders with multiple divisors. So, for example, suppose my target space was A2, or maybe P2, because I want something proper projective. And my curve did something like this. I had, again, one marked point here, P mapping to this point here. But now you have two divisors. So here, the stalk n bar x f of p is n squared, because you have two divisors, you have to record the order of vanishing of functions along. And up will now map us to n. And this will send 1, 0 to A, 0, 1 to B for some A and B. And these are the contact orders with the two divisors. So even in complicated situations where we have many, many divisors, this combinatorics of this contact order, so map from this monoid to n, really is just recording the order of vanishing or contact order with all the different divisors going through the point f of p. So that's the first point, is that contact order records this richer information. Second point is that now this definition of contact order does not or continues to work, I should say, works even when f of c lies in D. So as I said, that was a fundamental problem in defining contact order in this, even in this simple situation, this classical situation here. Defining contact order was easy as long as the curve doesn't fall into D, but as soon as it falls into D, you have trouble. But the point is that this definition now doesn't require, the definition of UP says nothing about whether or not C falls into D. So this is something that makes sense in any event, and essentially solves that problem about what happens when the curve falls into the divisor. Okay, so to make a long story short, let me just state this as a theorem using myself and Siebert and such a Bramish Chen. There exists a good moduli space in stable log maps, and it carries a virtual fundamental class. So in other words, we can do Gromov-Witten theory in this context. Okay, so that is part of the story. I defined in the last lecture notion of contact order. I just talked about curves having contact orders, where the contact orders were given by elements of these cones of the tropicalization. So this sort of helps with quite a bit of the definition that we needed in the last lecture. But you might remember there was also one other point, which is that we had to allow negative contact order. And so far, if you look at the way contact order is defined, contact orders always take values in N. So those should be thought of as being non-negative contact orders. So the question is, how do we actually define negative contact orders? So we now have to soup up this story a little bit more. We have to talk about punctures. This is what we call punctured from Witten grants. And this is due to Bromwich, Chen, myself, and Siebert. And so the idea is that we are going to allow ourselves to enlarge log structures and curves a little bit. So just wondering in terms of time, the most sensible way of proceeding is. Given I have 6 more pages of notes in 15 minutes. Well, let me just proceed with the definitions. I'm at least being honest. So, definition. Let's C to W, log smooth. Family of curves. And write the MC in the following way. So it's going to be MC direct sum over OC star of the, so here I'm going to use some notation, P1 through Pn. So this means this is the divisorial log structure for C with the divisor D being P1 through Pn. And sorry, I should remove the C here. And so Cm is the log structure without any mark points. So here what I do is I take the direct sum of these two copies of these log structures. This is one way to think about the mark points, is you're just adding into the log structure, adding in functions that can vanish at the PIs. You identify this direct sum over OC star just means we identify the copy of OC star in here with a copy of OC star in here. So this is one way of writing MC. So then puncturing of MC is a log structure MC circ on C with MC circ. This will be a sub sheaf of monoids of M direct sum OC star. And here I put the group of this sheaf of monoids. So the group means that we're allowing ourselves to invert elements of this. So in other words, if we have a function which vanishes at pi, we're going to throw in the inverse of that function. So we're suddenly allowing poles as well as zeros. So we'll have poles at p1 through pn. And this should satisfy a couple of properties. MC should be a subgroup or submonoid of MC circ. And alpha C circ of everything that's not an MC. Well, maybe I should say alpha C circ restricted to MC equal to alpha C. And alpha C circ applied to MC circ minus MC. Everything that's in MC circ but not an MC should be zero. Okay, let me try to give the basic idea here of what's going on. Let me do a simple example of this. Let's take C to be equal to, say, P1 with log structure pulled back from the standard log point. So in other words, what I have is here's my P1 mapping down to W, which is spec K with K star cross N. So I have sort of everywhere along here, I have an N in my sheaf M bar C, but I'm going to add one mark point, P. So here the monoid is N squared. So you can think of, so locally, sections of MC look like something pulled back from the base, namely, essentially a invertible function phi. So we'll have some invertible function phi times something pulled back from the base, which I'll write as 1 comma a, times some, if I have a local coordinate t here, times some power of b, of t, of the coordinate t, where b can be any positive or negative number. So in other words, I'm allowing poles. But the crucial thing is that I'm only going to allow a pole when alpha, the structure map, takes this to 0. So in a sense, I mean, I can't define the structure map alpha on T inverse because alpha of T inverse will have a pole. But as long as this gets mapped to 0, note we can define alpha of phi 1 comma a to the b as being 0 as long as a is greater than 0, because the alpha w of 1a is then equal to 0. So in other words, I'm allowed to have some pole at the point P as long as alpha takes the rest of this stuff coming from the base to 0. Okay, so again, I appreciate that's kind of a little bit short on time for motivating properly. But what is the main point? we define puncture log maps as before. As like stable log maps. Now with domains being punctured. Log curves. So now contact orders are a little bit more subtle. Again, we have P and C cert puncture point. So with M bar X F of P gives us a map. We have a map of F bar flat. So this is given F from C cert to X puncture map. We now get a map on the level of M bar C at P. And by construction, this is contained in M bar W pi of P plus Z. So recall before, this was just equal to M bar W at pi of P plus N. And now it's contained, and we can project onto the second factor, and we get a map to Z. So this now allows, this is our contact order UP, and this now allows negative values. So it's this enlarging the log structure a little bit suddenly gives us the freedom to impose negative contact orders. So rather than rushing through what looks like 4 more pages of notes, which I'm not going to do, I think I'd be better off just ending with sort of a little hint. I have a feeling that this is probably very hard to absorb in the course of one lecture. What I want to do is give a couple examples of what kind of behavior you get, and then call it a day. So let's take, as usual, I'm going to take a X with a smooth divisor D. Let's take D to be isomorphic to P1 and X a surface, and D squared being -1. So I have, as a domain, I can take a P1 with 1 mark point, and I can map that isomorphically to D. And it's possible to define this as a puncture map, where I have to add a little bit to the log structure. Here's not just the mark point. I can get, so F can be defined as a punctured map, so that it has contact order -1. At P. So one way to think about this is that there's an intersection number between this curve class is actually D, and the divisor D, so the intersection number is -1. And what we're doing is we're keeping track of the intersection number by somehow saying, well, it's all going to happen at this one point. This one point has contact order -1, hence explaining why the curve class has intersection number -1 with the divisor D. And then one more example, a very similar example. Let's now take X a surface, D again equal to P1, but this time maybe I'm going to take D squared to be equal to 2. Now I want to take as domain something a little bit more complicated, and take as domain a reducible curve, something that's unit 3 components. and this time with 4 points. I'm going to do this with contact order 2 and -1, 2 and -1 at the 4 points. And it's possible to do this, to define a map here, so the image is just a copy of D, with this irreducible component of C mapping isomorphically to D, and then these components getting contracted. So these will get contracted to points here and here. Okay, now if you notice, if you take a look at the sum of these contact orders, 2 plus 2 minus 1 minus 1 is 2, and that accounts for the intersection number of the curve class represented by this map, that curve class being D, the intersection number of that curve class with the divisor D, which is 2. That's how it shows these contact orders. Okay. Now, this can be deformed in 2 different ways. So the first way is that I can simply deform the image of this irreducible component of the curve. So in other words, I can deform the curve here, and I still have these 2 components being contracted. Any component, in order to have negative contact order, the curve can't look like this. All right, such a curve always has positive contact order at these points. But these irreducible components are being contracted. They're falling inside the divisor. And as long as a component falls inside, entirely inside the divisor, having negative contact order is possible. So we still have this sort of contracted, let me just try to draw it in here, it's contracted, but we can't really see it. It can't deform away. Another thing I could do is actually just smooth the domain. So I have D, and the domain still maps isomorphically to D, now with the 4 marked points, marked puncture points. Okay, so here we smooth, so here we're deforming image of the middle irreducible component. And here we smooth domain. And I can no longer move this curve away from D. The reason is that, as I said, if you have a point with negative contact order, the corresponding irreducible component of the domain has to fall entirely inside the divisor. So I no longer have the freedom to move this out to something like that. And so, in fact, these are really deformations of this curve in different directions. So this shows some of the subtlety. The modular space is actually single in this case. So, in fact, the modular space of such curves is singular for combinatorial reasons, really. So this actually generates a lot of interest in the theory, and there are many different subtleties, but we do get a good theory, and we can, at the end of the day, define those negative contact order invariants we needed last time to define the intrinsic mirror. And we can also use these, and this is what I want to talk about, but don't have time. We can use these to also define a consistent wall structure. So let me end by some statements. Results. One, these give nice invariance, which can be used to construct the intrinsic invariant ring. And secondly, these invariants can be used to construct consistent wall structures. Now, I did want to get the time to actually talk about these consistent wall structures because it shows the real power of these puncture invariants and of this tropical way of thinking I introduced. But unfortunately, I think it's probably just too much to hope to get across in these lectures. So I think I will end there and see if there are questions.